So now that we know what a heuristic is, we come to the branch and bound design technique. So why I mentioned heuristic here is because this design technique uses heuristics. So there are three main steps: branching, bounding, pruning. Branching is, of course, the same thing you did in backtracking. Your problem, you will model it in the form of a state space tree. So we had this password guessing problem. You had three characters, they have to be binary and all that. So you denoted it as three variables, x1, x2, x3, whatever. You drew a state space tree with 0 dash dash 1 dash dash. The next level you had 0 0 dash 0 1 dash and so on and so forth. So you constructed the state space tree, you drew branches and all that. That is exactly what is going to happen here also. You model a problem which is given to you, like say a word problem, as a state space tree, and you depict the branching, the split up. That is branching. Bounding is, at every step we will use something called a heuristic function to obtain an upper bound or lower bound. So if it is a maximization problem, we will obtain an upper bound. If it's a minimization problem, we will obtain a lower bound. Bound on what? On whichever quantity we are trying to maximize or minimize. So for example, if it is the knapsack problem, knapsack, I hope you know, is a maximization problem. You are expected to maximize the total value you have. So what you will do is, at every step of the branching, we will first have a heuristic function framed. We will compute the value of that function at every step of that branching, and we will get an upper bound on the maximum profit that can be obtained if I am taking this branch. So for example, knapsackla, you can choose to either take item A or not take item A. So from start, you can see two branches, A or not A. So if I take A, what is the maximum profit I can obtain by any combination of subsequent items? I will compute this using the heuristic. Similarly, if I do not take A, what is the maximum profit I can obtain using any combination of the remaining items? I'll compute this. So let's say I have some value for, let's say I have a value 75 when I include A, and 45 when I do not include A. And remember this, I will explain the heuristic function in detail now. We are going to look at the knapsack example, but what I mean by the maximum value I will obtain when I take A is not just the value of A itself. I have taken A, so that value is with me already, and then for the remaining, I can use the remaining items in any legal combination. Out of all possible combinations, what is the maximum I can reach? So let's say you have 4 items, A has been taken. The remaining you can take B alone, C alone, D alone, B, C, C, D, B, D, B, C, D, depending on your weight and other constraints. Of all these combinations, which gives me the maximum. Similarly, on the other hand, A excluded, I either take B alone, C alone, D alone, B, C, C, D, B, D, B, C, D, whatever, which gives me the maximum. So there is a logic, exact mathematical expression which we will look at, but the idea is you get an upper bound on what is the maximum profit I can obtain if I pick this, if I don't pick this. Then you compare the two upper bounds, whichever is better, you will take that. So this is a maximization problem. So if your upper bound on one branch is 75 and on another branch it is a 45, obviously you will prune the branch which gives you a 45, and you will only take the 75 branch. Again from there you will split. I have taken A, now I will either take B or not take B. Again at every step you will compute that function. You will choose whichever has the greater bound, so on and so forth. You will continue until you reach an answer state. So that is the bounding, computing the bound. And pruning is where you reject the suboptimal state. So this is the broad overview of what happens in a branch and bound algorithm. It will become clearer when we look at an example.